Have you ever wondered what the fastest thing in the universe is? Many of us know the answer: light. Light travels at an incredible speed, about 300,000 kilometers per second. It's so fast that nothing with mass can ever hope to catch up. This is a fundamental rule in our universe, a cosmic speed limit set by Albert Einstein's famous theories. It seems like a simple rule that nothing can break. But what if I told you there's a place in the cosmos where the rules get a little bit weird? A place where space itself is forced to move faster than light. This mind-bending idea isn't just a fantasy. It's a consequence of the most extreme objects we know of: black holes. Specifically spinning black holes. When a massive star dies and collapses, it can form a black hole, a point of infinite density with gravity so strong that not even light can escape. This strange and fascinating region around a spinning black hole has a name: the Ergosphere. The name comes from the Greek word ergon, which means work. This is a fitting name because, as we will see, it is a place where you can actually extract energy from the black hole itself. The Ergosphere is not the black hole, nor is it the point of no return, which is called the event horizon. Instead, it is a buffer zone, an oval-shaped region of space-time that surrounds the event horizon. Think of it as the chaotic, swirling water around a drain before it finally disappears down the hole. It is a place of transition between our normal universe and the ultimate unknown. What makes the Ergosphere so unique is the extreme effect of frame dragging within it. As the black hole spins, it literally drags the fabric of space-time with it. Inside the Ergosphere, space-time is moving faster than the speed of light. The existence of the Ergosphere forces us to reconsider our relationship with space. We tend to think of ourselves as moving through space, but in the Ergosphere, it is space that moves us. Inside the Ergosphere, you cannot remain at rest with respect to a distant observer. The boundary of the Ergosphere is called the static limit. Outside this limit, you could theoretically use powerful rockets to hold your position and resist the drag of space-time. However, the moment you cross the static limit and enter the Ergosphere, that possibility vanishes. For instance, it is theoretically possible to send a probe into the Ergosphere, have it drop some mass, and then have it emerge with more energy than it started with. This process, known as the Penrose process, effectively mines energy from the black hole's rotation. So what exactly is this Ergosphere? In simple terms, it is a very special region of space that exists only around spinning black holes. The word Ergosphere itself comes from Greek roots, ergon, meaning work, and sphera, meaning sphere. Imagine a massive spinning ball submerged in a thick liquid like honey. As the ball rotates, it would drag the honey around with it, creating a swirling vortex. A spinning black hole does something similar, but instead of dragging honey, it drags the very fabric of space-time itself. Think of it like being caught in a whirlpool that is spinning faster than you could ever hope to swim. It's a cosmic conveyor belt from which you cannot step off. The Ergosphere is defined by two important boundaries that separate it from the rest of the universe and the black hole's core. The outer boundary is known as the static limit. This is the edge of the Ergosphere. So, if space inside the Ergosphere is moving faster than light, does this violate one of the most sacred rules of physics? However, the Ergosphere exploits a clever and perfectly legal loophole in the cosmic law book. Imagine you are on a very long conveyor belt that is moving at 10 kilometers per hour. You can walk on this conveyor belt at a speed of 5 kilometers per hour. When you walk in the same direction as the belt, your total speed relative to the ground is 15 kilometers per hour. This idea was first proposed by the brilliant physicist Roger Penrose in 1969. He imagined a process now known as the Penrose process that could effectively mine energy from the black hole. This concept transforms the Ergosphere from a mere curiosity into a potential cosmic power plant of unimaginable scale. Imagine you send a probe into the Ergosphere carrying a package. Once inside, the probe splits into two pieces. Because of the bizarre physics inside this region, it is possible to jettison the first piece in such a way that it has negative energy relative to an observer far away. In essence, you are using the black hole as a gigantic flywheel, tapping its kinetic energy to power your escaping probe. Could civilizations of the far future harness black holes for power? To understand how space can move faster than light, we first need to change how we think about space itself. Most of us imagine space as an empty, motionless void. But Albert Einstein's theory of general relativity revealed a very different picture. He showed that space and time are woven together into a single dynamic fabric called spacetime. Think of placing a heavy, spinning bowling ball into a vat of thick syrup. As the ball rotates, it would pull the surrounding syrup into a swirling vortex. A spinning black hole does exactly this, but the syrup it drags along is the very structure of reality. The closer you get to the spinning black hole, the more intense the frame dragging becomes. Inside the ergosphere, this space-time current becomes overwhelming. Every strange region in space needs a boundary, and the ergosphere is no exception. Its outer edge is called the static limit. Imagine you are in a spaceship equipped with unimaginably powerful rockets. However, the moment your spaceship crosses the static limit and enters the ergosphere, the game changes entirely. Once you are inside this boundary, the battle is lost before it even begins. You can still move around within this flow, much like a person on a fast-moving train can still walk up and down the aisle. It's a cosmic conveyor belt from which you cannot step off. So, if space inside the ergosphere is moving faster than light, does this violate one of the most sacred rules of physics? Albert Einstein's special theory of relativity famously states that nothing with mass can be accelerated to the speed of light, let alone exceed it. Let's use an analogy to clarify this crucial distinction. Imagine you are on a very long conveyor belt that is moving at 10 kilometers per hour. The ergosphere works in a similar way, but on a much grander cosmic scale. In fact, we see this in the expansion of the universe, where distant galaxies are receding from us faster than the speed of light because the space between us and them is expanding. This is the beautiful loophole created by general relativity. The story of the ergosphere does not begin with a telescope, but with a pen, paper, and the brilliant mind of Albert Einstein. In 1915, he published his theory of general relativity, completely revolutionizing our understanding of gravity. Just a few months later, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's equations, describing the spacetime around a non-spinning spherical mass. This solution gave us the concept of a black hole and its event horizon, a truly remarkable achievement. This question was answered in 1963 by a New Zealand mathematician named Roy Kerr. He discovered a new solution to Einstein's equations that described the spacetime around a spinning, uncharged black hole. For many years, the Kerr black hole and its ergosphere remained a mathematical curiosity, a fascinating but unproven consequence of Einstein's theory. Today, we know that most, if not all, black holes are spinning, and therefore they should all possess an ergosphere. The science behind the ergosphere is rooted in a fascinating concept known as the lens-Thirring effect, or more commonly, frame dragging. To visualize frame dragging, imagine Earth spinning in space. According to Einstein, its rotation should be twisting the space-time around it ever so slightly. In 2004, NASA launched the Gravity Probe B mission, a satellite designed specifically to measure this tiny twist. After years of collecting data, the mission confirmed the lens-Thirring effect with remarkable precision, proving that space-time does indeed get dragged along by a rotating body. Now imagine replacing the Earth with a black hole spinning at nearly the speed of light. The frame-dragging effect becomes unimaginably powerful. It is no longer a subtle twist, but a violent, inescapable vortex of space-time. The discovery of the ergosphere's existence through Roy Kerr's solution opened a new chapter in theoretical physics, but it was the physicist Roger Penrose who in 1969 revealed its most astonishing potential. He devised a thought experiment, now known as the Penrose process, to show how one could theoretically extract energy from a spinning black hole. The process relies on a peculiar feature of the ergosphere, the existence of negative energy orbits. Penrose imagined sending a particle or a capsule into the ergosphere. Once inside, this capsule would split into two pieces. It provides a theoretical mechanism that could power some of the most energetic phenomena we observe in the universe, such as the powerful jets of plasma that are often seen erupting from the centers of galaxies. The science of the ergosphere, unveiled by Penrose, shows us that even from a place of no escape, energy can be set free. Imagine you are in a futuristic spacecraft, cautiously approaching the static limit of a spinning black hole. The immense gravity of the black hole would act as a powerful lens, warping and distorting the light from everything behind it. As you pilot your ship across the static limit and into the ergosphere, the first thing you would notice is not a sight, but a feeling, an irresistible and unyielding pull. Your ship's navigation systems would scream warnings as they fail to maintain a stationary position. Looking out your window, the universe you knew would seem to be in motion. The distant stars, once fixed points, would begin to drift and swirl around you. The sky would be divided into two distinct parts. In one direction you would see the familiar star field, though now it is warped and swirling. In the other direction you would see the profound and absolute blackness of the event horizon. Light from stars in the direction of the spin would be energized, a process known as beaming. This would make them appear intensely bright and blue-shifted, their light concentrated into a brilliant narrow cone. Conversely, light from stars in the opposite direction, against the flow of space-time, would be de-energized and red-shifted. The gravitational lensing would continue to create multiple images of single stars, scattering them across your field of view like cosmic mirages. The experience would be profoundly beautiful but also deeply confusing. The universe would appear to be a chaotic storm of light. This visual chaos is a direct window into the physics of the ergosphere. You are not just seeing stars, you are seeing the direct, tangible effects of space-time being twisted and dragged at relativistic speeds. The sky becomes a map of the gravitational field, with every warped star and every shifted color a data point revealing the incredible power of the spinning black hole that holds you in its grasp. Perhaps the most dominant feature of your view would be the event horizon itself, the inner boundary of the ergosphere. It would appear as a perfect circle of absolute blackness, a hole punched through the fabric of reality. This boundary would be framed by a thin, bright ring of light, the photon sphere. This is an orbit so close to the black hole that photons can travel in circles, creating a permanent, brilliant halo around the abyss. As you are swept along by the current of space-time, your view of this central darkness would change. Because you are forced to co-rotate with the black hole, the event horizon would appear to spin relative to the distant stars. The bright, blue-shifted stars would seem to be chasing the fainter, red-shifted ones in a perpetual celestial race around the central void, a race choreographed by gravity. If there were any matter falling towards the black hole, such as an accretion disk of gas and dust, the scene would become even more spectacular. This material would be heated to millions of degrees, glowing with incredible brightness as it spirals towards the event horizon. Ultimately, what you would see from inside the ergosphere is the raw power of gravity made visible. You would be a spectator to a cosmic light show powered by the twisting of space-time itself. The ergosphere is more than just a mind-bending curiosity. It serves as a unique and invaluable laboratory for scientists. It is a place where the laws of physics are pushed to their absolute breaking point, allowing us to test the predictions of Albert Einstein's theory of general relativity in the most extreme environment imaginable. In our everyday world, gravity is a relatively weak force, and the effects predicted by relativity, like time dilation and the curvature of space, are incredibly subtle. But in the ergosphere of a spinning black hole, these effects are magnified to an enormous scale, becoming the dominant forces that govern reality. By studying the ergosphere, even from afar, physicists can explore the intricate relationship between gravity, space, and time. Every distorted star image, every jet of plasma, and every gravitational wave that originates from these regions carries with it information about the twisted space-time. The ergosphere also allows us to probe the connection between general relativity and quantum mechanics, the two great pillars of modern physics. It is a place where the macro world of gravity and the micro world of quantum particles meet. And by observing their interaction, we may one day unlock the secrets of a unified theory that can describe the entire universe. The ergosphere is not just a passive testing ground for our theories. Scientists believe it plays an active and crucial role in powering some of the most energetic and spectacular events in the cosmos. Many of the supermassive black holes found at the centers of galaxies are not dormant. They are surrounded by vast accretion disks of gas and dust, and from their poles, they often launch colossal jets of plasma that travel at nearly the speed of light. The Blanford-Znajek mechanism, a process related to the Penrose process, suggests that the rotational energy of the black hole, harnessed through its ergosphere, is the engine behind these powerful jets. This twisting of magnetic field lines acts like a gigantic electric generator, creating powerful electric fields that accelerate particles away from the black hole's poles, forming the jets we observe across the universe. This concept transforms the ergosphere from a theoretical curiosity into a fundamental component of galactic evolution. These powerful jets pump enormous amounts of energy back into their host galaxies, influencing how stars are formed and how the galaxy itself grows and changes over billions of years. Moreover, the ergosphere could be a source of some of the most powerful explosions in the universe, known as gamma-ray bursts. The study of the ergosphere continues to push the boundaries of what we know and what we can imagine, acting as a gateway to future scientific breakthroughs. Telescopes like the Event Horizon Telescope, which captured the first ever image of a black hole's shadow, are beginning to resolve the fine details of the environment just outside the event horizon. The burgeoning field of gravitational wave astronomy offers another exciting window into the ergosphere. When two black holes merge, they send ripples through the fabric of spacetime. By analyzing these signals with detectors like LIGO and Virgo, scientists can measure how fast the black holes were spinning and infer the size and influence of their ergospheres. Looking to the future, the ergosphere remains a place of profound mystery and opportunity. Could the Penrose process be harnessed by an advanced civilization for an almost limitless supply of energy? These thought experiments, born from studying the ergosphere, stretch our imagination and encourage us to ask bold questions about what might be possible in the universe. Ultimately, the ergosphere matters to science because it embodies the spirit of exploration. It represents a frontier where our current knowledge ends and the great unknown begins. The ergosphere is a testament to the fact that the cosmos is filled with wonders that are far more bizarre and magnificent than we could ever have conceived. And it continues to inspire scientists to keep looking, questioning, and striving to understand the deepest secrets of reality. We began this journey with a seemingly impossible question: can space itself move faster than light? We have traveled to the very edge of reality to find the answer, exploring the bizarre and captivating region known as the ergosphere. This cosmic whirlpool, spun into existence by the rotation of a black hole, is a place where the fabric of space-time is dragged into a current moving faster than light. The ergosphere is one of the most profound predictions of Einstein's theory of general relativity, a testament to the strange beauty that emerges from his equations. Our scientific exploration has transformed the ergosphere from a mere mathematical curiosity into a tangible and vital part of our cosmic understanding. Yet for all we have learned, the ergosphere remains shrouded in deep and compelling mystery. These questions drive astronomers and physicists forward, pushing them to build better telescopes and devise cleverer ways to probe these enigmatic regions from afar. The ergosphere is a powerful symbol of how much we still have to learn about the fundamental forces that shape our reality. It stands as a silent, spinning monument to the fact that the cosmos is filled with wonders that continue to elude our complete comprehension, waiting for the next generation of curious minds to uncover their secrets. As we conclude our journey, we are left with a sense of profound awe. The ergosphere is a powerful reminder that the universe is far stranger, more dynamic, and more magnificent than we often perceive. It is a place where the familiar rules of motion and energy are completely rewritten, governed by the elegant yet mind-bending principles of general relativity. The story of the ergosphere is also a story about the power of human curiosity and scientific inquiry. It began not with a direct observation, but with abstract mathematics on a page, a theoretical prediction born from the relentless pursuit of knowledge. From Roy Kerr's solution to Roger Penrose's thought experiments and the ongoing work of astronomers with instruments like the Event Horizon Telescope, our understanding has been built step by step. What other wonders lie hidden in the equations of physics, waiting to be discovered? What other extreme environments exist in the cosmos, pushing the boundaries of what we believe is possible? The ergosphere is likely not the final frontier of strangeness in our universe. It is a gateway, an invitation to keep asking bold questions and to never lose our sense of wonder about the world around us. So the next time you look up at the night sky, remember the ergosphere. Remember that out there, in the darkness between the stars, there are places where space itself is spinning faster than light. Because in the quest to understand the universe, every question we ask and every mystery we ponder brings us one step closer to comprehending our own place within this grand cosmic dance.